question 4 asks us to find a way to distinguish between these 5 compounds. Now, when you get questions like this, it's important to realise that what you're going to get tested on is not just getting the right chemistry in there, but having a good, logical, systematic approach to doing it. So what you've got to do is come up with a sequence of tests which make a good story, with a sequence of identifying things and then taking them out of the picture and focusing on the ones that are left, narrowing it down further, and finally ending up with all of the answers. So there's no unique way of doing it. So I'll just give a suggestion, but there would be lots of possible alternatives. So looking at these, one place you might start would be by noticing that 2 of them are aldehydes, A and E, and the others are not. And aldehydes are always a good place to start because Tollens reagent reacts specifically with those, so we'll be able to pick those 2 out straight away. So let's do that. So what we want to do is to say, right, step 1 is to add warm Tollens reagent to each. Okay, so we can just do the same thing to each of them, and as we know, what Tollens does is it forms a silver mirror with aldehydes. So we'll say A and E form a silver mirror, and the others just don't do anything, but you have to say that. You can't just imply it. So we write down the others don't react. Okay, so that's our first test. And then you say, right, so now let's focus on A and E and think, right, how can we distinguish those 2? And the key thing is that this is a phenol, whereas that's a normal benzene ring, and easiest way to distinguish those is to remember that that OH group activates the benzene ring. So remember, the lone pair on the oxygen delocalizes into the ring, increases the electron density, and to cut a long story short, allows it to react with bromine without a catalyst. That one, there'll be no reaction. So that's easy because bromine is coloured, and so you'll be able to see the colour change. So let's do that one. So step 2 is to add aqueous bromine to A and E. Not to all of them, because there's no point looking at how these ones interact with bromine. We're going to differentiate those in a different way. So make it clear that it's just to A and E that we're going to do this test, and the answer then is that E will decolorize it, or change it from orange to colourless if you prefer. A doesn't react. So at that point we have identified A and we've identified E, because we narrowed it down to those 2 and we now know which one is which. So you should then say that, so that it's very clear in your working that you've now done the job as far as A and E are concerned. So A and E have been identified. Okay, so now we've got to turn our attention to B, C and D, and there are various ways of proceeding, but quite a good one is to notice that that is a ketone, these 2 are alcohols, and to remember that 2,4-DNP is a very useful reagent because it reacts specifically with aldehydes and ketones. We've already taken the aldehydes out of the picture, so it's going to specifically pull out our ketone. So let's go for that one. So we're going to number 3, add 2,4-DNP to B, C and D. And the positive result there, remember, is aldehydes and ketones form a yellow or orange precipitate with 2,4-DNP. Other things just do nothing. So that's what we can say, is that B forms a yellow or orange precipitate. And the others don't react. Okay, so that's our third test. With that one, the full name of 2,4-DNP is 2,4-dinitrophenylhydrazine. If you can remember that accurately, you can write it down. If you can't though, just use the initials, because if you get the name wrong, they might be awkward, and even if they really know what you're getting at, they might claim, or whatever compound it is you've named wouldn't react, and so they'd mark it wrong. So don't tempt the name unless you're really sure. Just use the initial. 2,4-DNP or 2,4-DNPH is also acceptable. Okay, so that's specifically identified B. So again, we should tell them that, so that they know that you've done the job now for B as well. So that's A, B and E done. So we've now got C and D to identify. So they're both alcohols, but what you hopefully noticed is that this one is a secondary alcohol and this one is a tertiary alcohol. And the big difference, remember, is that this one could be oxidized to a ketone, this one cannot be oxidized. So the test to use is with aqueous acidic potassium dichromate. Again, make sure you get the reagent right. If you just say add potassium dichromate, neither of them would react. It doesn't work without the acid, so you have to say the acid. So, and again, you also have to warm it, so you should say that really. So warm C and D with aqueous potassium dichromate and sulfuric acid. Okay, so that's the test, not just adding potassium dichromate. You're not going to get the mark for that. You've got to state what actually works, which is that. And that will oxidize C, but again, just saying it oxidizes or reacts, that doesn't count. You've got to say what happens. So we can say that C will turn the solution from orange to green, which remember is the characteristic colour change with dichromate. And D has no reaction. So D doesn't react. And so that's then it. Job done. With that one, you may be tempted to talk about refluxing or distilling, all that kind of stuff, which remember is an issue with dichromate, but that's when you're using it as a preparative method. When you're trying to make a sample of a compound, you have to worry about that. But here we're not interested in what the product is, we're just asking the question, does it react or not? So don't suggest using complicated methods. You just warm it in a test tube and you'll see the colour change for this one and no colour change for that one. In all of these questions, they've got to be simple test tube reactions. As soon as you suggest anything more complicated with, as I say, methods like reflux or whatever, or methods involving measuring things like melting points, they're not going to give you marks for that. Okay, so that is the end of it. So we've just got to round that off by saying that C and D have been identified. Okay, so as I say, you probably had to use pretty much those tests, I think, but you could have done it in various orders and that would be fine, so long as you made clear at each stage what the test involves, which ones you're applying to, so to each of them in this case, to A and E in that case and so on. That needs to be clear. What the positive outcome is, but also say that the other ones don't react. And when you've narrowed it down and identified a specific one, make that clear. If you do all of that, they can't help but say, yeah, that's very logical and clear, and they will have to then give you full marks. B asks us to consider this compound, which was compound E, and just to suggest what would happen when it reacts with each of these four reagents. So Tollens reagent we've already mentioned, reacts specifically with aldehydes, but the point is you have to know for Tollens what it actually does, and it acts as an oxidizing agent, so it does the same thing as dichromate does. And if you think about it, it has to be that, because Tollens reagent contains Ag+, and it gets converted to metallic silver, hence the silver mirror, and so you can see that the Ag+ has been reduced, therefore the aldehyde must be oxidized. And when you oxidize an aldehyde, you get a carboxylic acid. So the compound will have phenol group, that hasn't got any reaction, so that bit's unaffected. You can't oxidize phenols easily, it's important to know that. So dichromate again would have left the phenol alone, but it will oxidize the aldehyde to a carboxylic acid, so that's the Tollens one. Bromine, aldehyde's not interested, but the phenol group is, because the OH group, lone pair on the oxygen, delocalized into the ring, increases the electron density and therefore activates the ring for electrophilic substitution. And what you have to remember is that because the ring is now activated, it's liable to react more than once, and activating groups, electron releasing groups like OH, direct to 2, 4 and 6. So you're going to get not just one but 3 substitutions, and so you're going to get this compound with the OH still there. You haven't replaced the OH. The job of the OH was just to activate the ring, and that branch is just sitting there not getting involved, but you get the 3 bromines substituting in at 2 and 4 and 6, and so you get that compound. The third one, sodium hydroxide. That can be a tricky one because it does various things, some of which we haven't reached yet in the course. But with aldehydes, as far as we are concerned at A level, it doesn't do anything. But with phenols it does, because remember, phenols are weakly acidic. And of course that's the most obvious thing sodium hydroxide could do, is be a base. And so if you have an acidic compound like a phenol, it can just form a salt. So the compound that's formed has the ring and this bit unaffected, but the OH group now functions as an acid, which means it loses H+ and replaces it with the metal ion from the base, so we get O-, Na+ is the salt. When you draw that, be careful, make sure, actually with the OH as well, but with this one, which is perhaps less familiar, make sure that the bond connects still to the oxygen. If you draw a covalent bond to sodium, it's always going to be wrong, because sodium doesn't do that. So you've got to make sure you draw it like that. And you don't have to put the charges in, but it's helpful to do that because it just reminds you that it's an ionic product that's being formed. And the last one, NaBH4, you need to learn as a specific reducing agent which reduces aldehydes and ketones back to alcohols. So it's not going to do anything to the phenol group, but it's going to reduce that aldehyde back to a primary alcohol, and so your product will have the phenol bit of the molecule intact, but this part, instead of double bond O, will now just have the primary alcohol group, like that. So you always get questions like that, and it just underlines the point that with organic chemistry you have to learn the reactions thoroughly. Know what the reagents are, what they do, practice drawing the structures accurately, and then the actual figuring out is not at all difficult. Organic chemistry is mainly about having secure knowledge, and that's what you've got to work on. Building it up all the time, making it more and more secure, so that when you get to the exam in the summer, it's just there. Okay, and that was the end of the test.